continuing our study of the integers. In this video, we're going to look at two systems called z sub m and u sub m. So first, just a reminder that if m is an integer greater than or equal to 2, and x is any other integer, then we have a shorthand for the remainder when x is divided by m, right? It's x mod m. And this remainder is always non-negative and less than m when you're dividing by m. And now z sub m is shorthand for the set of all possible remainders when an integer is divided by m. And as we know from this previous paragraph, the remainder when you divide by m must be one of the integers 0 through m minus 1. So that's what z sub m is. Quick example, z sub 7 consists of the integers 0 through 6. Those are the remainders you can get when you divide by 7. And now we're going to define two operations on this set z sub m. A little typo here, this z should have a subscript m. So as usual, we're assuming m is an integer greater than or equal to 2. And now we're taking two other integers, a and b. And a plus sub mb is defined to be the remainder when a plus b, ordinary addition, is divided by m. So you could say that in pretty short form using our previous notation. A plus sub mb is a plus b mod m, the remainder when a plus b is divided by m, and times sub m is similar. A times sub mb is the remainder when a times b is divided by m, or a times sub mb is a times b mod m. So one thing to notice is that you can do this for any two integers, a and b, but we will usually be interested in the case where a and b are elements of z sub m. And now we'll try a few examples. 5 plus sub 7, 4. According to the definition, is 5 plus 4 mod 7. And 5 plus 4 is 9. And 9 mod 7 is the remainder when you divide 9 by 7, which is 2. Second example is pretty similar. 34 plus sub 5, 72. By definition is 34 plus 72 mod 5. 34 plus 72 is 106. 106 mod 5 is 1. So as I said a few minutes ago, we will usually be applying plus sub 5 only to numbers in Z5. But it is possible to apply plus sub 5 to any two integers, as we did in this second example. And here's another example where we are using plus sub 5 on two integers which are not in Z5. Minus 4 plus sub 5 minus 8. So according to the definition, this is a minus 4 plus minus 5 mod 5. And minus 4 plus minus 5 is minus 9. So you may remember that calculating the remainder when a negative number is divided by a positive number like 5 is a little tricky, but we did several of those problems, and the answer is 1. And the reason is when you write minus 9 as a multiple of 5 plus a remainder, a non-negative remainder smaller than 5, it's minus 2 times 5 plus 1. The remainder is 1. Here's a more normal example. Looking at times sub 7. 4 times sub 7, 4. Definition, that's 4 times 4 mod 7. 4 times 4 is 16. And 16 mod 7, the remainder when you divide 16 by 7 is 2. 7 times sub 9, 4. Same kind of calculation. That is 7 times 4 mod 9, or 28 mod 9. And the remainder when you divide 28 by 9 is 1. So one thing to notice here is that for all integers a and b, whether or not a and b are in z sub m, if you add them using plus sub m or multiply them using times sub m, the answer will always be in z sub m. So in particular, if you start with two numbers that are in z sub m, say a and b, then a plus sub mb and a times sub mb will be in z sub m. And using our earlier terminology, this means that z sub m is closed under the two operations plus sub m and times sub m. Add two things in z sub m, you get something in z sub m. Multiply two things in z sub m using times sub m, you get something in z sub m. So sometimes this is expressed by saying that the plus sub m and times sub m are operations on z sub m. Now what we would like to do for the next few slides is compare z sub m and these two operations that we just talked about with the ordinary integers and the operations of addition and multiplication. But before we start doing that, there are two really helpful tools for working with these two operations, plus sub m and times sub m. And we'll be using them quite a bit in the remainder of this set of slides. The first tool is the eliminating mod m lemma. And it says that if you have an integer a and an integer m greater than or equal to 2, then you can write a mod m as a plus some integer times m. There will always be some integer t such that a mod m is a plus t times m. So if you're dealing with an expression that involves a mod m, you know it can be replaced by a plus t times m, where t is some integer. So here is a very brief proof. We know that if you divide a by m, you get a quotient of a div m. Remember, this is our shorthand for the quotient. A div m times m with a remainder of a mod m. This was our notation for the remainder. So if you solve this equation for a mod m, if you solve this equation for a mod m, we see that a mod m is a minus a div m times m. The t that works, the t that works is minus a div m. So here's an example. According to the eliminating mod m lemma, 341 mod 7 can be written in the form 341 plus some multiple of 7. And we want to find the t that works. So to find the t that works and to find 341 mod 7, this is the remainder. Remember, this is the remainder when you divide 341 by 7. We will divide 341 by 7 using the division algorithm. So 341 is 48 sevens with a remainder of 5. Here is 341 mod 7. And now if you solve this equation for 341 mod 7, in other words, solve for 5, you get that 5 is 341 plus minus 48 times 7. So the t that works in this case is minus 48. And now the second lemma, the inserting or deleting multiples of m lemma. So here we are starting with 3 integers a, k, and m, with m greater than or equal to 2. Under those circumstances, a plus k times m, that quantity mod m, is the same as a mod m. In other words, if you have a multiple of m added inside a mod m, you can get rid of it. So this lemma really says that inside a mod m, you can insert, in other words add, or delete, in other words subtract, multiples of m, and you will not change the value of the expression. So here's one way we could use the inserting and deleting multiples of m lemma. I want to find minus 11 mod 5. Well, I know that inside this mod m, I can add or subtract multiples of 5 without changing the value of the expression. So I'm going to add 5s. Could use the division algorithm to do this, our sort of long method for finding a negative number mod 5. But I'm going to add multiples of 5 inside the mod 5 until I get a positive number. So minus 11 mod 5, according to the inserting and deleting multiples of m lemma, is minus 11 plus 5 mod 5, which is minus 6 mod 5, which, according to the inserting and deleting multiples of m lemma, is minus 6 plus 5 mod 5, which is minus 1 mod 5. Applying the inserting and deleting multiples of m lemma once more, minus 1 mod 5 is minus 1 plus 5 mod 5, which is 4 mod 5. And we know that 4 mod 5, the remainder when you divide 4 by 5, is 4. Well, it took a long time to do this, but it doesn't take a very long time if you're doing the calculations mentally. And what I'm using here is the fact that for any integer k, non-negative and less than 5, k mod 5 will be k. So now on this slide is the argument for the inserting and deleting multiples of M lemma. So we're going to argue that A plus K times M mod M is A mod M. And we're assuming the hypotheses of the lemma that A, K, and M are integers and M is greater than or equal to 2. So the first thing we do is divide A by M using the division algorithm. So we know that you can divide A by M, and you will get A equals some quotient Q0 times M plus a remainder R sub 0, and R sub 0 is non-negative and smaller than M. And our notation for the remainder, reminding you once again, is A mod M. Okay, now we're going to work with A plus Km, the thing inside the mod M on the left-hand side of this equation we're trying to argue for. So the first thing we're going to do is, in A plus Km, we're going to replace A by Q0M plus R0. Right, this is the result of dividing A by M. So if we simply make that replacement, we get A plus K times M is Q0 times M plus R0 plus K times M. Now we do a little rearranging. We're going to put the two M terms on the right-hand side together. So on the right-hand side, combining the Q0 times M and the K times M and factoring out an M, we will have the quantity Q0 plus K times M plus R0. And we're going to use Q1 for Q0 plus K and R1 for R0. So this is equal to Q1 times M plus R1, where Q1 is Q0 plus K, and R1 is R0, which, remember, is A mod M. Well, in this equation, we have A plus Km written as an integer times M, plus a number, a non-negative number less than M. By the uniqueness part of the division algorithm, there's only one way of writing A plus Km in this form. And that one way is A plus Km is the quotient when you divide A plus Km by M times M, plus the remainder when you divide A plus Km by M. So this quotient must be the Q1 from this equation. In other words, the quotient A plus K times M div M must be Q1, which is Q plus K, and more importantly, the remainder when you divide A plus Km by M, in other words, the quantity A plus Km mod M must be this remainder R1, which is R0, which is A mod M. And this final equation with the two middle terms removed is what we were trying to prove. Okay, so now here is sort of a theoretical example of how we might use the two lemmas and the definition of times sub M and plus sub M. So I want to argue that this equation holds for all integers x, y, z, and w, and we are assuming that m is an integer greater than or equal to 2 as usual. So we're starting with the left-hand side. And we'll be working from the inside out, sort of, using the definitions of plus sub m, times sub m, and we'll be using the two lemmas. So here we go. The left-hand side is equal to x times y mod m plus sub m z times w mod m. What have I used here? I've used the definition of times sub m. Right? X times sub my, by definition, is x times y mod m, and similarly for z times sub mw. And now I am using the eliminating mod m lemma. I know that xy mod m is xy plus t1 times m for some integer t. And similarly, I know that zw mod m is zw plus t times m for some possibly different integer t2. And now we are about to use the definition of plus sub m. How do you apply plus sub m to two integers? You add the two integers, according to the definition, and take the result mod m. So this simply uses the definition of plus sub m. Now we'll do a little bit of algebra inside the mod m. We will basically combine the two m terms, t1 times m and t2 times m. So if we do that and factor out the m, we get the quantity xy plus zw plus t1 plus t2 times m, that whole thing mod m. And now we are using the inserting and deleting multiples of m lemma. We're going to use it to delete this multiple of m. The final result, xy plus zw mod m, which is the right-hand side of the equation we were trying to prove. Okay, here's another property of the integers, which, as we'll see, also is true of the set z sub m. So the property of the integers that I'm talking about here is that for every integer x, there's an integer y, namely y equals minus x, such that x plus y is 0. And the corresponding statement is also true in the system z sub m plus sub m and times sub m. Although the additive inverse of x in z sub m won't be minus x, as we'll see. So for example, 4 is in z sub 7. What element of z sub 7 do you add to 4? Using plus sub 7 to get 0? The answer is 3. 4 plus sub 7, 3 is 7. And 7 mod 7 is 0. So the additive inverse of 4 in z sub 7 is 3. It's the number you add to 4 using plus sub 7 to get 0. So how do you find the additive inverse of something in z sub m in general? So assume you have an a in z sub m. Remember, this is the set of integers 0 through m minus 1. Well, if a is 0, then the additive inverse of a is 0. This is the easy case. And the other case isn't much harder. If a is not 0, then the additive inverse of a is going to be m minus a. So for example, when m was 7, and we were looking for the additive inverse of 4, we could have calculated 7 minus 4 and gotten the 3. So I'm leaving it to you to verify that a plus sub m, the quantity m minus a, is 0. This should simply use the definition of plus sub m. And I'm leaving it to you to verify that if you take something in z sub m which is non-zero, then m minus that thing is also in z sub m. Also an easy thing to verify, just manipulating some inequalities. Okay, moving on to another property of the real number system. If x is a real number which is not equal to 0, then there's another real number, namely 1 over x, which when multiplied by x will give you a 1. The number 1 over x is called the multiplicative inverse of x. So this kind of thing happens for some of the non-zero values of x in z sub m. So in other words, for some x's in z sub m, there is a y in z sub m for which x times sub my is 1. Some x's in z sub m have multiplicative inverses. And if this happens, we call y the multiplicative inverse of x in z sub m. It won't be 1 over x, because ordinarily 1 over x will not even be an integer, and therefore won't be in z sub m. Here's a quick example. If you take, we're looking at z21, and if you multiply 5 times 17 using times sub 21, according to the definition, that's 5 times 17 mod 21. 5 times 17 is 85. And 85 mod 21, the remainder when you divide 85 by 21 is 1. So 5 has a multiplicative inverse in z21, namely 17. And 17 has a multiplicative inverse in z21, namely 5. And now we want to look at the question how you determine the x's for which this happens. And if it does happen, if x does have an inverse, how do you find the inverse? So we're going to look at those two questions. I'm going to give you the answer to the two questions, the answers to the two questions, and the proofs will come later. So the answer to the first question is, an element of z sub m has a multiplicative inverse in z sub m if and only if the greatest common divisor of m and x is 1. So if we're looking at a z15, for example, the integers between 0 and 14 inclusive, whose greatest common divisor with 15 is 1, will be the elements that have multiplicative inverses. That's 1, 2, 4, 7, 8, 11, 13, and 14. All of these elements of Z14 should have multiplicative inverses. I'm sorry, all these elements of Z15 should have multiplicative inverses in Z15. We'll see how you can find them in just a minute. So what elements of Z15 don't have multiplicative inverses? Well, those would be the numbers between 0 and 14 inclusive, such that if you take the greatest common divisor with 15, you get something bigger than 1. Those would be the integers divisible by either 3 or 5. So 3, 5, 6, 9, 10, and 12 are the numbers in Z15 which do not have multiplicative inverses. And now on to the second question. How do you find the multiplicative inverse once you know there is one? Well, if m is not too big, say m equals 12, for example, you can find the multiplicative inverse of an element by trial and error. So if I were looking for the multiplicative inverse of 2 in Z15, 15 isn't too large either. So the greatest common divisor of 15 and 2 is 1. So 2 has a multiplicative inverse in Z15. So I would simply try multiplying 2 by the elements of Z15. Using times sub 15, right? 2 times sub 15, 1, 2 times sub 15, 2, 2 times sub 15, 3, and so on until I got an answer of 1. And I did that. I won't give you all the details. But when I finally got to 8, when I tried 2 times sub 15, 8, I got an answer of 1. But if m is large, then trial and error is a pretty inefficient method. So here's a more efficient method for finding the multiplicative inverse of an element of Z sub m, assuming you know it exists, which means we're assuming that the greatest common divisor of m and x is 1. This will take us back to a calculation we did earlier. Let's see. Yeah. So I'm going to, as we go through this, I'm going to try this with m equals 11 as an example. Even though 11 is fairly small, it'll make the example easier. And we will be looking for, in our example, we'll be looking for the multiplicative inverse of 8 in Z11. We know it exists because the greatest common divisor of 11 and 8 is 1. And since the greatest common divisor is 1, we know by Bézout's lemma that 1 can be written as a linear combination of 11 and 8. There are two integers s and t for which 1 is equal to 11s plus 8t. And we saw how to do this calculation in one of our previous modules. So I'm going to do this. I've done the calculations, and I found that 1 is 11 times 3 plus 8 times minus 4. The s is 3. The t is minus 4. A little typo here. The s should be 3, but the t is minus 4. So actually, this typo will not affect what we do in the next step. So I'm just going to ignore it. The multiplicative inverse of 8 in Z11 is the value of t mod 11. So the t that you find, in our case it was minus 4, is what you use to find the multiplicative inverse of 8. You take t mod 11. So minus 4 mod 11 is, I'm using the inserting and deleting multiples of m lemma. It's equal to minus 4 plus 11 mod 11. Minus 4 plus 11 is 7. Mod 11 is 7. So the multiplicative inverse of 8 in Z11 is 7. And you can check. The check is easy. You simply multiply 8 times 7 using times sub 11. And we see that the answer is 1. Let's try another example with a larger m. This is sort of a random choice. 1079. And I will be looking for the multiplicative inverse of 265. I found that the greatest common divisor is 1. And now I'm going to use the Bezout's lemma calculations that we did earlier to write 1 as a linear combination of 1079 and 265. When I did that, I got 14 for the s and minus 57 for the t. Right, 1 is 1079 times 14 plus 265 times minus 57. The 14 we can ignore. It's the minus 57 that we use to find the multiplicative inverse of 265. Minus 57 is the t. So the multiplicative inverse is t mod 1079, or minus 57 mod 1079. I will, inside this mod, I will add 1079 using the inserting and deleting multiples of m lemma. This sum is 1022. And 1022 mod 1079 is 1022. This is the multiplicative inverse of 265 in Z sub 1079. And then the check isn't too bad. I'm assuming you can do this on your calculator. We would be calculating 265 times 1022 mod 1079, and you do get a 1. So here is the theorem. For all integers m greater than or equal to 2, so this is our usual assumption on m, and for all integers x not equal to 0, these two statements are equivalent. The greatest common divisor of m and x is 1, and number 2, which says x has a multiplicative inverse in z sub m. Number 2 says there's some y in z sub m, which when multiplied by x using times sub m gives you a 1. So this is the theorem. So this is going to be fairly important for us. So I want to say it in a slightly different form, using sets. I'm simply going to say that the set of x's for which number 1 is true is the same as the set of x's for which number 2 is true. We have two ways of characterizing these elements x that have a multiplicative inverse in Z sub m. And we're going to prove that part 2 follows from part 1. Showing that part 2 implies part 1 requires a different proof, which we're going to leave for discussion in the exercises. Okay, so we're proving part 1 implies part 2. In other words, we're proving that if the greatest common divisor of m and x is 1, then x has a multiplicative inverse in Z sub m. So we are going to assume that the greatest common divisor of m and x is 1, and we will construct the inverse of x, pretty much like we did in our examples. So we're assuming the hypotheses m and x are integers and m is greater than or equal to 2, and we're assuming the greatest common divisor of m and x is 1. And we use Bézout's lemma to get integers s and t, such that s times m plus t times x is 1. And now we're going to show that this number t, mod m, that will be an element of Z sub m, is the inverse of x. And we will do it by multiplying t mod m by x using time sub m and seeing that we get 1. Okay, so t mod m times sub m x, and we are using the eliminating mod m lemma here. T mod m is t plus some integer multiple of m. And now we are using the definition of time sub m. So multiplying two things using time sub m means that you multiply the two things and take the answer mod m. And then inside the mod m, we're just doing a little bit of algebra. We're multiplying through by the x. So we get t times x plus k mx. And now we're going to use the inserting and deleting multiples of m lemma to delete this multiple of m inside the mod m. So the multiplication gives us t times x mod m. And now we are going to insert a multiple of m. This is the inserting and deleting multiples of m lemma again. Inside the mod m, we can insert or delete any multiple of m. So we're inserting s times m. And s times m plus t times x is 1. So this is 1 mod m, which is 1. So this completes the proof. We've just shown that t mod m multiplied by x using time sub m gives you 1. So what we've been looking at in the last few slides are the elements of Z sub m that have multiplicative inverses. These are called the units of Z sub m, and we use the notation U sub m to stand for the set of units in Z sub m. So U sub m will be the set of numbers, integers in Z sub m, such that the greatest common divisor of x and m is 1. And just an example or two, U sub 10 consists of the numbers 1, 3, 7, and 9. These are the numbers between 0 and 9 inclusive, whose greatest common divisor with 10 is 1. We have to leave out any integers that have either 2 or 5 as a divisor. U7, every number between 1 and 6 taken with 7 and getting the greatest common divisor gives you an answer of 1. So as we move into more abstract algebra, Z sub m and U sub m are going to provide a lot of examples for us.